Okay, hello everyone. I'm Ashwinee. I'll be presenting this work on private fine-tuning of LLMs with zeroth-order optimization. So this is some joint work with colleagues at Princeton, DeepMind, and FAIR. So the sort of paradigm that we're considering in this work is one where you're working with a pre-trained LLM that is already very, very good. It's seen a few trillion tokens of data from the internet, and it knows how to do lots of things. And if you want to use it for a particular task, you need to adapt it, which means you just need to nudge it in a little bit in the correct direction. So when we do this, you may have some privacy concerns with the data that you need to adapt to specifically. And of course, this is a pretty flawed paradigm to consider. I'll just say that up front. You may have heard of this well-known work, this position paper. And they point out some of the issues with this paradigm where you just assume that your pre-trained model pretty much magically already knows what you need to do, and you have some private data and you only care about the private data. Regardless, this is the paradigm that we'll be presenting this work in, but this is just sort of the context to consider. We are able to do a lot of things in this work that you might be surprised at because we're working with models that are already very good. So when we think about adaptation, of course, your classical method here is DP-SGD. I'm going to take a gradient on a sample in my data set, clip that gradient, and then add noise to the aggregate batch gradient. And this works. People have been using it, but it has some issues. I'll get into those issues later, but now I'll just present some other kind of methods here. So DP-SGD is one specific first order method. There are first order methods, second order methods, and there are also zeroth order methods. So I'm not going to talk too much about any specific zeroth order method in this talk. In the paper, we go through multiple zeroth order methods because there's a lot of them. The oldest one we consider is like some 40 years old or something. And I'd like you to think about this more as a framework for privatizing different zeroth order optimization methods. So at a high level, without going into too much math yet, you can think about something like this. So I'll sample some random vector. So maybe it's just -1s and 1s at every dimension in my model. And this can be sampled from basically any distribution. We try a few different ones. And I'll also have some batch of data points. And for each data point in my batch, I'm going to ask, would you rather take a step in the direction of this random vector or away from this random vector? And so each data point is going to give me one bit, either yes, I want this, or no, I don't want it. And I take all of these votes, and I'm just going to put them into a histogram with all the other data points, and I can privatize this histogram any way that I want to, really. So my update for this one step is that I generated some random vector, and by asking each of these data points whether this vector was good for them or bad for them, I'm going to come up with one bit, -1 or 1, and then I'll take a step scaled by that random vector that I had predetermined and selected some time ago. This is one zeroth order optimization method, but there are a lot of zeroth order optimization methods. You might have heard of this one. This is SPSA, simultaneous perturbation stochastic approximation. It was popularized in some work last year from some of our friends at Princeton. And what this method does is it takes a scalar step, which is the difference in losses between, again, taking a step in the direction of a random vector or away from that random vector, as normalized by the scale of the step that you're taking. And previously, our private information was a bit, and so we had our array of private voting methods. And here, it's a scalar, so we can privatize it with our array of private mean estimation methods, Gaussian mechanism, Laplace mechanism, what have you. And it might be surprising to you that taking literally a random vector and doing a bunch of random vectors is sufficient enough to get good performance fine-tuning large language models. And that's because fine-tuning large language models is really, really easy. They basically already know how to do the task that you've given them because they just saw it in the pre-training data and pretty much memorized it. And you just need to kind of poke them a little bit and, say, hey, remember, you've already seen this data set before. So why don't you just go ahead and, tell me the answers? So that's why fine-tuning these things is so easy. But we'll talk about, some alternatives to this later on. So here's another private zeroth order method. You take the scalar and then you add some noise to it. And you're adding noise to the scalar instead of the full parameters of the model, because the update to the full parameters, the direction of that, is given by this random vector. And the only thing that you need to privatize is the magnitude. So here's just another sort of visualization of what this looks like. We have these purple lines here, which represent these random directions. And the better one, as according to our data, is given by this red line. And then we'll add some noise along this. So you can imagine that, well, our algorithm already started off being quite random, and we are adding some more noise. This magnitude can change. It can even flip in the other direction. But we started off with something that is quite random already. So maybe the noise that we're adding is not going to hurt so much. We'll talk about how we can use various kinds of mechanisms with this, and also what some of the advantages of this might be. In terms of privacy analysis, of course, this is an iterative method. So at each iteration, I'm going to do this private histogram or this private mean estimation, what have you. And I'm going to do this for some number of iterations and just compose them using my regular techniques, whether I'm doing approximate DP or pure DP. And we're going to do all the regular stuff that you would expect to do if you're doing differentially private machine learning. We're just going to replace the first order method with the zeroth order method. So now I'll get into some results. First, this method looks pretty random already. So I think it's a fair question to ask. What happens if you try and do some kind of membership inference attack on this method? So we're going to try and do some privacy auditing on this method and on DP-SGD. And we're going to use, this privacy auditing framework that has, been done by Thomas and some other folks. And we're going to basically add in some canaries that we come up with, and we're going to see what happens. So this result, I think, is pretty interesting. So we're comparing Zio and SGD here. And if you look at the rightmost column, you'll see how much of a privacy audit we're able to get when both methods are fully non-private. So against SGD, our membership inference attack, of course, has like a 100% success rate. And so the only constraint on the empirical value of epsilon that we can get from our audit is just how many canaries we add into the data set. So we could make that empirical value of epsilon like 100 if we wanted to. We just have to add in a lot of canaries. And however, for the zeroth order method, even without doing any kind of privatization, you'll notice that our membership inference attack is not actually perfect. In fact, the empirical lower bound that we get, so this is a confidence interval saying that with a 99% confidence, I believe that the empirical privacy leak is at least this much. So we can get around 1 for this zeroth order method without any privacy. And that's the same value that we get for DP-SGD if we do have some weak level of privacy, like epsilon equals 10. So it's interesting that as we go along the various levels of privacy, in fact, this zeroth order method tends to have a stronger level of privacy protection than the first order method. I think that's interesting. So this is kind of the first open question here. We have this fairly random algorithm. Can we analyze its inherent privacy guarantees in any way? We didn't do that. So the stuff I'm going to be talking about is just adding privacy normally. But I think this is something interesting potentially to think about. And the reason why I think it's interesting to think about is that this zeroth order method, if you privatize it and assume that it doesn't have any inherent privacy protection, still does about as well as your private first order method. And if you were able to somehow show that it has an inherent level of privacy, you would be beating the first order method in general. So this is just a quick ablation across model size. So the x-axis, we have the number of billions of parameters of the model that we're fine tuning. And as the model gets better, it seems that the gap in performance between our method and the baseline seems to shrink a bit. That was for approximate DP, but you might want a pure DP guarantee. We don't think about this too much in DP-ML because we tend to say that the Gaussian mechanism will never fail catastrophically. And indeed, it probably won't. But if you follow recommendations that say we should have a cryptographically small value of delta, then you may as well just go ahead and have no delta with a pure epsilon DP. Now, DP-SGD doesn't really like this, doesn't really like the use of the Laplace mechanism because it doesn't really like the L1 norm as a sensitivity measure. But our zeroth order method has no real issue with this. And if for any reason you wanted to use pure epsilon DP, I think this is a pretty interesting alternative. DP-SGD doing absolutely nothing here, no matter how much privacy budget we give it, really. Another interesting point here is the memory savings that we can get from a zeroth order method. So any kind of first order method has to save activations as it goes through the model. So here we're doing a bunch of memory saving tricks like nice little CUDA kernels, activation checkpointing, etc., mixed precision training, whatnot. Regardless, there's a limit to how much you can handle with a first order method because you have to save some activation vector that basically looks like the width of the model times the depth of the model times the total number of tokens that you want to process at once. And this is a pretty hard limit. And even if we do PEFT methods like LoRA, it doesn't really seem to be the case that we can get much out of DP-SGD on these resource constrained devices. Even if you're not too resource constrained, if you have like A100s, there's still a limit to how much data you can train on with DP-SGD. These zeroth order methods naturally don't need to save activations because they're not going to compute gradients. So as soon as they go through a layer, they can just throw away all of the information completely. And if you're willing to do some, shenanigans with kernels and chunking and fused things that we do here, you can scale these methods almost arbitrarily to however many data points you want to process. So that's cool, but some things that are not so cool is how well these families of methods scale with data. So most of our results are done with 1,000 training samples, and there's a good reason for this. And it's that this method doesn't really scale very well if you increase the amount of data that it has. So naturally, if we have difference for privacy, then the larger our data set is, the better our subsampling, and we're just going to add less noise as a result of that. But the actual non-private method, the zeroth order optimization, doesn't really change at all if you increase the number of data points from 250 to 5,000. The only reason that we do better in DP is just the amplification via subsampling. So zeroth order optimization isn't very good with samples. And if we think about the amount of information that we're getting from each data point, kind of obvious why. Literally, each sample is only contributing 1 bit. So adding more data is not going to get you very much. Data diversity really is not a thing here. And indeed, if we compare our zeroth order approach to SGD in different data settings, we'll see that as we start increasing the data, of course, our first order method is going to have plenty of information to get from each data point. And our zeroth order method is basically going to cap out pretty early on. And if you have really any reasonable data size at all, you probably should not be using this because the zeroth order optimization just doesn't scale very well with data. So improving the data efficacy in zeroth order optimization would be interesting. And I think I will pretty much leave it at that. There are some reasons why you might want to use this. There are some reasons why you might not want to use this. And I think that there are some open questions. There's also another paper that in fact does the same thing as we do at this very workshop, which is fun. Yeah, I will leave it at that and take questions.
Yeah, thanks for the talk. Yeah, I was just had one question. So in this, when you're comparing DP zeroth order to DP-SGD, what are the hyperparameter choices? Like how many steps and so on? Like are they individually optimized for each?
Yeah, we do a lot of hyperparameter optimization, like a lot, more than probably anyone reasonable would do. But we wanted to get really good DP-SGD baselines for some other papers where we also use DP-SGD as a baseline. So it was sort of shared effort across multiple papers. So we tune iterations, learning rates. We do like LoRA. We tune the rank in LoRA as well. There's a lot of hyperparameter ablations that go into this. Yeah, I would say it's a pretty good baseline because on any of these tasks that we evaluate on, I think our numbers are probably the highest that you'll see somewhere.
So I'm generally curious, like how many more steps do you need for the zeroth order method?
Oh, yeah. So I think I have this somewhere. Yeah. Okay. Yeah. So we need about 10K steps for like a 0th order method. And for SGD, you might need a few hundred, probably less than 1,000.